What does a rose, t-shirt, and highlighters have in common? These are everyday items that you might not think twice about. All of these items, however, have been dyed, naturally or synthetically. So what exactly are dyes? Dyes are a natural or synthetic substance that is used to add color to or change the color of something. Today there are powder dyes, food coloring dyes, paints, and many other forms of dyes. The discovery of dyes led to the creation and growth of the biggest chemical company today, the dye industry. So how were dyes discovered? Where did this all begin? The earliest written use of dye stuff on dye clothing was in China in 2600 BC. The Chinese made the earliest attempts of chemistry. Dyes were derived from roots, leaves, barks, and berries. Over time, humans discovered new ways to dye everyday objects. Blue, red, and yellow. You might take these colors for granted, since you see them every day and they seem so common. All of these colors have a long history, however. Blue was a very sought-after color in the early ages. Blue shades were not common in plants. The only plant where blue was found was an Indigofera tinctora plant, which comes from the legume family. This plant was named after the Swedish botanist Linnaeus. Indigofera tinctora grows to be 6 feet tall and grows in tropical and subtropical climates. Blue also comes from other temperate regions from Isoteris tinctora, which is the oldest dye plant of Europe and Asia. In Britain, it is known as wood, and in France as pastel. 700 years ago, Marco Polo saw indigo being used in the Indus Valley and named it indigo. Indigo, however, was prevalent before Polo saw it in Southeast Asia and Africa. People were dyeing their clothes and fabrics with it. The indigo plant is not blue, however. It must undergo chemical process before the blue dye is made. Fermentation under alkaline conditions followed by oxidation make the blue dye. This process was discovered by multiple cultures when the plant leaves were accidentally soaked in urine or covered in ashes and then left to ferment. In this process, the indigo color is reduced and changes from blue to yellow. Then it dissolves in the alkaline solution. The fiber is worked in the solution. When it is exposed to the air, it turns green. Then the air changes the green into deep and rich blue, indigo. Indigo has a precursor compound called indokinmal, which contains an enclosed glucose unit. A derivative of blue is purple. Terran purple was worn by Roman senators, Egyptian pharaohs, and royalty. Terran purple is an indigo molecule that contains 2 bromine atoms. This color was obtained from an opaque mucus secreted from borax. Similar to indigo, oxidation makes this color. The bromine in the color is found in the mollusk. Myth says that Hercules observed his dog's mouth turning a purple color after eating some shellfish. Purple is said to originate from the Mediterranean port city of Tyre in the Phoenician Empire, now part of Lipidum. 9,000 shellfish are needed to produce 1 gram of Tyrian purple dye. People obtain the dye by cracking the shells of the mollusk by using a sharp stick and extracting a small vein-like gland. Cloth was saturated with a treated solution of the gland and then exposed to the color for the color to develop. The dye would turn yellow, then green, then blue, and finally purple. In 1865, synthetic blue dye was discovered by Johann Friedrich Wilhelm Adolf von Baer. He investigated the structure of indigo. In 1880, he found a way to make indigo in the laboratory from easily obtainable materials. It took 17 years, though, before synthetic indigo was actually created. Bayer's first synthesis of indigo required 7 separate chemical reactions. This was the beginning of the decline of the natural indigo. So how do we even see the colors through our eyes? The molecular structure of the compound allows the absorption of certain wavelengths of light from the physical spectrum. The actual color of the dye we see depends on the wavelength of the visible light that is reflected back rather than absorbed. If all the wavelengths are absorbed and no light is reflected, then the color of the cloth we see is black. If no wavelengths are absorbed, all the color is reflected and we see the color white. If only the wavelength of red is absorbed, then we see the complementary color, which is green. The relationship between wavelength absorbed and the chemical structure of the molecule is similar to the absorption of sunscreen products. That is, it depends on the presence of double bonds alternating with single bonds. For the absorbed wavelength to be seen in the visible range, there must be a greater number of alternating double bonds than single bonds. Finely ground minerals and other organic compounds have been used to make color pigment due to absorption of certain wavelengths of visible light. Red is made from the roots of the madder plant, which is part of the Rubidae family. This plant contains a dye called alizarin, which is used in India. Red is also obtained from morant dye. This is dye where another chemical metal ion is needed to make that color into a fabric. When mixed with the aluminum morant ion, a rose color is created. When mixed with the magnesium morant ion, a violet color is created. When mixed with the chromium morant ion, a brownish violet is created. When mixed with the calcium morant ion, Alexander the Great used the bright red in his army. He defeated the Persian army because they believed that Alexander's army was weak and they fought with mercy. The alizarin molecule is presented in the bright red. Bright red, also called turkey red, was color fast and bright. To make the red color, fabric was boiled in potato soup with olive oil, aluminum chalk, and treated with sheep dung and tin salt. Alizarin, which is responsible for the color red, is a derivative of anthracene, which is found in insects, plants, and fungi. This chemical is not colored. It must go a chemical process for it to be colored. Two OH groups on the right ring of alizarin combined with the alternating double and single bonds in the rest of the molecule provide enough conjunction for the alizarin molecule to absorb visible light. The OH groups are more important than the number of rings. Another anthrax derivative is carnic acid, which is scarlet. This is obtained from crushed beetles of male corneals. This molecule obtains numerous OH groups. This color was used in the New World by the Aztecs and by the Redcoats in the American Revolutionary War. Correct fuel, also known as carmine, was expensive. It required 7,000 insect bodies to produce 1 pound of the scarlet color. Today, 80% of the world's population of dye is made in Peru. This is equivalent to 4,000 tons. There are many derivatives of xanthan. Jagun is a brown color. It is found in walnuts. Lawson is a reddish orange color and is found in hennas. Angstrom is a reddish color that is found in sand dollars. Carmesic acid is bright red. This color, however, did not go far into being popular and being commonly used. Up to the 20th century, there was a contract needed in England to produce fabric with a scarlet color. This government supported the industry. The last of the primary colors is a bright yellow-orangish shade that comes from saffron crocus. Saffron is obtained from the stigmas of flowers, the part that catches pollen for the ovary. The crocus was native to the eastern Mediterranean. It was used by the Minoan civilization of Crete in 1900 BC. It was also used in the Middle East and in the Roman Empire as a spice, medicine, perfume, and dye. The need for this yellow color declined during the Industrial Revolution because of the stigmas from the plants needed to be individually removed and no one had time for them. Also, the color was not a very color fast or long lasting. When man-made dyes were created, the saffron industry faded away. Saffron is still grown in Spain, where it must be hand-picked to this day. Today it is used for flavoring and food coloring. It is also used in the Spanish dish called panela and in the French dish bullabulus. 13,000 stigmas are needed to produce 1 ounce of this dye. The organic molecule responsible for this yellow-orangish color is crocetin. So next time, look around you and admire the dyes on your clothes, in your pen, or even outside. You'll be surprised to see how much chemistry is around you.